Okay, let's do our example number 3. So what is provided here is the geometry of the structure. So we have two members of a truss that are connected at point B by pin connections, and we know that the distance, the length of BC is 4 feet, and we know that the distance between the two connections is 3 feet. We also know the property of the materials. We know the graph. So we know that in tension, that will be the curve of our stress strain curve, and in compression, that will be this one. So you see very different behavior in tension and compressions. That's why you have the two different information. And we also know the cross section. So we know AB, the cross section is 1.5 inches square. And we also know that BC, the cross section is 1.25 inches square. Okay, so we can imagine that the force in BC is way larger than in BA, and that's why the sections of BC is larger, so we decrease the stresses. So the question is, what is the maximum force P that we can apply to that structure? So we stay in the elastic zone. So just be careful. I twisted a little bit the problem I found, and I want you to stay in the elastic zone. So we will do in parallel all the calculation for the bar AB and the bar BC. So I will put a AB member and BC member, and we will make all the steps. So the first things that we can check is which one is in compression, which one is tension. So the first P is pulling down, so it's compressing AB. So AB will be in compression, and BC will be in tension. If we do the free body diagram at point B, we will have the force P that we don't know. We will have the force AB that will go up because he has to balance the force P, so up and right, and the force BC will be to the left, so will be in compression. Remember that this is the force on the joint, so AB, the member is pushing on the joint, so the joint is pushing back on AB, so this is compression, and this one, that will be tension. So this is for the first information. Second information, what will be the ultimate, the yield strength? The yield strength. So AB is in compression, so we are on that curve there. Whoop, whoop. And we want to stay in the elastic zone, so we have to stay there, all the way there. So my yield strength will be 18 kilo square inch, kilopound square inches square inch. For the tension, we will be on the small curve there, and you see we pull and it break right away. So there's no plastic zone at all. So we are in 5 kilo square inch for this one. Okay, let me do this and this. What do we need? We need to find the relation between the force P and the member. So we are a little free body diagram to the right. Let me move that up a little bit. And we need to work on that free body diagram. And we know that we have a 3, 4, 5 triangle there. So if we do the sum of the forces on y equals 0, we have minus P plus FAB times, so this is the y-axis, so 3 divided by 5 equals 0. So FAB equal, we want to write the forces in terms of P, or the forces in terms of, yeah, that doesn't matter. Anyway, I will write it in terms of P. So FAB equal P, and I move over the 5 and the 3, so 5 divided by 3. Here we go. So force AB will be 5 divided by 3 times P. And if we do the sum of the forces on X equals 0, we have minus FBC plus FAB equals 0. So we have FBC equal FAB, oh, not FAB, sorry. Sorry, I forgot the 4 divided by 5 plus 4 divided by 5. This is just the complement on X. So FBC equal 4 divided by 5 FAB, and I replace FAB by 5/3 of P. So I got FBC equal 4/3 of P. So 4/3 of P. Okay. So, so you see what? The force in the member AB is larger. Oh, I talk about at the beginning with which one will be larger force. It's not because of that, it's because of the limits. The yield strength is way different in compression and in tensions. That's why we need different area. Okay, let's keep going and see where we go. So the force max in the bar, force max will be equal to what? We have sigma equal the force divided by the area. So the force max will be sigma times the area. So for the first one, that will be 18 times the area of AB is 1.5. So you see we have a very, very larger yield strength, so we can have a smaller area for the same force. So that will be 27 pound. What is the kilopound? I always forget to write that. Kilopound. Kilopound, I know it's not you get that. Keep. Okay, I always forget. Keep. And this one will be the 5 times the area. The area is provided there is 4.25. So that will be 21.25 kilopound. Okay. And now that we have the max force and we have the P, okay, so we have the force max in P, so we have, this force, the 27, so the force max equals something times P. So we found P equal the force max divided by the ratio that we found before, the 5/3 and the 4/3. So here, P will be equal to 27 divided by 5/3. 27, that will make us P max equal 16.2 kilopounds. And on this one, the force max will be 21.25 divided by the ratio 4/3. So P max, it's equal to 15.94 kilopounds. So yeah, I know. So now if we look at the two maximum force, we have P equals 16.2 and P equals 15.9. So the maximum force that could be applied will be the smaller one. So the max will be 15.9 kilopounds, and that will be the limits because of the member BC. Okay, but you see that the 16 and the 15.9, they are very close. That's what you want. You want to try to dimensions your members, piping, materials, anything, so they support about the same force, or like not the same force, but your structure overall support the same force. So for this problem, the final answer will be the maximum force that could be applied at the point B will be 19.9 kilopounds. And this is based on the property of the materials in tension and in compressions and the cross sections that were proposed at the beginning. So hope that makes sense. That's a good one. Bye bye.